My name is Thomas Howard. I'm a postdoctoral fellow at the CNRS, and I would like to talk to you about our novel solution for increasing the workspace of ultrasound mid-air haptic interfaces. These interfaces are tactile feedback devices that use an array of ultrasonic transducers to focus acoustic energy towards small regions of their workspace, producing localized vibrotactile stimuli when these encounter a user's skin. By rapidly moving these focal points, it's possible to render vibrotactile shapes in 3D, allowing users to feel virtual objects. Because of their design, these arrays can only generate perceptible focal points within an elongated spheroidal region above the array plane. Basically, they feature a reasonably large vertical workspace, but quickly reach their limits in the lateral dimensions. This is often constraining in virtual reality, especially when users move around. There are two approaches for enlarging an array's workspace. The first entails increasing the array size or using multiple arrays. However, larger multiple arrays increase the complexity of the driving electronics, the power draw, and have a large footprint and cost. The second approach is to make arrays mobile to maintain the best possible fit between the array's workspace and a user's hand. There are two prior examples of this second solution. Sand and colleagues mounted a small array onto a VR headset, and Bryce and colleagues used a Baxter robot to translate an array, effectively increasing its lateral workspace. However, wearable arrays are obtrusive and limited by the direction in which the stimuli can be delivered relative to the user, while robotic manipulators introduce a significant added footprint and cost to the system. We followed the second approach, aiming to provide the largest possible increase in workspace without these limitations. To this end, we designed the PUMAH, a pan and tilt mount for focused ultrasound arrays which is easily adaptable to various array designs. The device is an aluminum and 3D printed bracket holding a support plate for the array and driven by a pair of servo motors allowing respectively 215 degrees of tilt rotation and 180 degrees of pan rotation. Once we calibrate the device position with respect to the virtual environment, the PUMAH rotates the array to orient it towards a tracked user's hand or interaction region, providing tactile feedback for virtual objects. We ran a user study to compare usable workspaces between a static array and the PUMAH. Users touched visual targets appearing throughout the virtual environment with their hand, and the array would attempt to generate a tactile stimulus at the target location. We then asked users to report whether they felt a tactile stimulus, and if so, whether it felt weak or strong. Sampling the workspace like this gave us an estimate of the volumes within which stimuli were perceptible at different intensity levels. Results showed that PUMAH could deliver perceptible stimuli in a volume up to 76 times larger than the static array's workspace. Despite inter-subject variability in tactile perception, the workspace within which all users systematically detected stimuli still increased more than 14-fold. Furthermore, repositioning the array plane parallel to the hand increased the perceived stimulus intensities compared to those delivered at the same locations by a static array. In conclusion, PUMAH is a simple, versatile, and low-cost device allowing massive gains in usable workspace for focused ultrasound arrays, increasing their suitability for VR interaction. As a final note, if you're interested in using or replicating our work, the PUMAH hardware designs and software tools are now open source and accessible on our GitLab. Thanks for watching.